bonds, we can say that in terms of bonds, we can say that there are two different bonds. First one is chemical bonds, and the second one is physical bonds. As you remember, chemical bonds, we have already studied chemical bonds as covalent bonds and ionic bonds and also metallic bonds. Okay. In addition to this, physical bonds can be also explained as weak interactions, and also uh, weak interactions and intermolecular forces. Intermolecular forces. Okay, so let's start with physical bonds, as the first one is hydrogen bonds. And the second one is van der Waals interactions. Okay, let's start with first the hydrogen bonds. Beside it, let me show you once again the difference between physical bond and chemical bond on the level structure of the water molecule. As you remember, water molecule can be represented by this level structure. And assume that the water molecules, it is in gas phase or liquid phase or solid phase, no problem. But in each phase, there is going to be weak interactions between the molecules. As you see that line with dots, these lines with dots can represent the physical bonds. Physical bonds. But as you remember, these are the chemical bonds. These are the chemical bonds. So right now we are going to focus on that physical bonds, and the first one is hydrogen bonds. Okay. Uh, For hydrogen bonds, there are two important elements, fluorine, oxygen, and nitrogen. This hydrogen bond is a specific physical bond. Uh, only includes that three elements with hydrogen atoms. With hydrogen atoms. You can also remember that as FON atoms. Okay. For instance, let's look at the first one. If you see fluorine atom in a molecule, and the hydrogen is directly bonded to fluorine atom, oxygen atom, or nitrogen atom, we can say that for the related molecules, there can be a hydrogen bond as an weak interactions. Let me show you with an example. Assume that, let's remember once again the same molecule, water molecule. Let's look at the water molecule once again. So, if you look at the water molecule, hydrogen atoms is directly bonded to oxygen atom. That's why between the oxygen atoms and hydrogen atoms in the different molecules, you can see a hydrogen bond between them. So, yes, it is a physical interaction, but especially an hydrogen bond. So, but if you look at another molecule, for instance, this is a diethyl ether molecule. If you look at that molecule, hydrogen atoms is not directly bonded to oxygen atom. If you look at that molecule clearly, you're going to see that hydrogen atoms is directly bonded to carbon atoms. That's why between each dimethyl ether molecules, you can't see any hydrogen bonds, because as you see here, hydrogen atoms is directly bonded to carbon atom. That's why no hydrogen, we can say that no hydrogen bonds between the diethyl ether molecules. Okay, this is very important. As you remember, once again, these hydrogen atoms should be directly bonded to fluorine, oxygen, or nitrogen atoms. This is the most important point to find the hydrogen bond. Okay, let me show you. Let me show you another examples. Let me show you another examples. If you look at the ammonia molecule, once again, hydrogen atoms is directly bonded to nitrogen atom. That's why we can say that between the same molecules we can see an extra hydrogen bond, and also you can also see it between hydrogen and fluorine. Hydrogen fluoride. In other words, fluoric acid. You can also see the same hydrogen bonds between the molecules. Okay, these are all dot products. These are all sorry, not dot products. These are all lines represented by dots here, hydrogen bonds between that molecules. Okay, this is the most important part of that hydrogen bond. In addition to this, hydrogen bond is the strongest one. Is the strongest one when you compare with other van der Waals interactions. Okay, this is the another important point. So if you ask me, I can say that hydrogen bonds is very easy to understand, but as I told you, you should understand that hydrogen atom is directly bonded to fluorine, oxygen, or fluorine, oxygen, and nitrogen atoms. Let me show you another molecule. Sometimes you can only see the general molecular formula. For instance, I'm going to show you. Assume that this is an alcohol. If you look at the alcohol molecule, we can call it as methyl alcohol. Methyl alcohol has oxygen and hydrogen atoms, as you see here. So if you look at the molecule structure of that methyl alcohol, hydrogen atoms are directly bonded to carbon atom, but also oxygen atom, and finally we can also see one hydrogen atom is directly bonded to oxygen atom. That's why, because of that part, that molecule can have hydrogen bonds. So, to summarize, I can say that especially in terms of organic molecules, alcohols, carboxylic acids, car
Hocam bir şey sorabilir miyim?
evet, evet.
Şey dediğinizi duymadım da bu yüzden hidrojen bağı olamaz dediniz. Ne için dediniz?
Yo, yo. That molecule can have hydrogen bonds dedim. Bu yüzden hidrojen bağı oluşturabilir. Ben mi yanlış?
Tamam ben yanlış duymuşum.
Aha.
Teşekkürler.
Pardon. So that's why, in terms of organic molecules, alcohols, carboxylic acids, and especially amides molecules can have hydrogen bonds, especially. Okay. So, when we are talking about the organic molecules, I'm going to emphasize once again that structures. In the next lectures, I'm going to show you more details about these molecules. So, we can say that because the hydrogen atom, because the hydrogen bond is the strongest weak interactions, we can also see that a molecule with hydrogen bond capacity may have greater greater boiling points. Boiling points. In addition to that information, you can show you different molecules. For instance, hydrogen, sulfur, and water. If you look at the periodic table, is oxygen. If you look at the periodic table, sulfur atom and oxygen atom, they are on the same group. If you look at the periodic table, for instance, assume that this is a periodic table. Oxygen is here and sulfur atom is here, and they are on the same 16th group. So, you may think that every chemical properties is nearly the same, but especially in terms of hydrogen bond, the boiling point,
Hocam, bekleme odasında biri var.
hemen bakıyorum. So, especially in terms of boiling point, if you compare with hydrogen, sulfur, or water molecule, boiling point of water is greater than hydrogen, sulfur because of hydrogen bond. Okay. So. Beside it, you can also compare the molecules with hydrogen bonds between them. Let's look at the ammonia molecule and water molecule. When you look at the ammonia molecule, let's remember its Lewis structure. If you look at the Lewis structure of ammonia molecule, there is only one lone electron pair on the nitrogen atom. But if you look at the water molecule, there are two lone valence electrons on the oxygen atom. That's why oxygen atom may have stronger hydrogen bonds than ammonia. That's why the hydrogen bond strength is greater on water molecule, and you can also see that the boiling point of water molecule is greater than ammonia molecule because of hydrogen bonds between them. Okay, so
Hocam, son kısmı bir daha eder misiniz lütfen?
Türkçe olarak mı anlatayım?
Evet, sadece son kısmı, karşılaştırma yaptığınız kısmı anlamadım.
Tamam. Şimdi şöyle söyleyeyim. Şimdi bir kere daha burayı şöyle bir silelim. Şimdi arkadaşlar, eğer ki şeye bakacak olursanız, kıyaslama anlamında bakacak olursanız, mesela hidrojen bağı oluşturanları da kendi içerisinde kıyaslayabilirsiniz. Mesela amonyak. Şimdi bu amonyak, bu da mesela su. Şimdi amonyağa bakıyorsunuz arkadaşlar. Nitrojen, evet, hidrojenleri bağladıktan sonra nitrojen atomunun üzerinde bir tane serbest elektron çifti var. Ama oksijen atomuna baktığınız zaman su molekülünde Onda iki tane elektron çifti var. Dolayısıyla nitrojen atomu tek başına şu elektron çiftleri nedeniyle bir tane hidrojen bağı oluşturabilirken aynı zamanda su molekülü iki tane hidrojen bağı oluşturabiliyor. O sebepten ötürü hidrojen bağları suda amonyağa göre daha kuvvetli ve tabii ki suyun kaynama noktası amonyağa göre benzer şekilde daha da kuvvetli, daha da yüksek diyebiliriz. Tamam.
Yani hocam kaynama noktasını karşılaştırırken bu ortaklanma elektron çiftlerine dikkat edebiliriz değil mi?
Yani aslında bunu özel örnekler üzerinden aklınızda tutsanız daha iyi olur. Çünkü bunu hidrojen bağı açısından molekül molekül incelemek lazım. Orada belirleyici başka faktörler de var tabii.
Hı, anladım.
O yüzden hani suyun bariz bir şekilde bunlardan yüksek olmasını suyun daha böyle çift hidrojen bağı kurabilme yeteneğine bağlayabiliriz. Ama tabii molekülün kompleksliği arttıkça farklı etkenler de devreye giriyor.
Anladım hocam,
Aha,
teşekkürler.
bir şey değil. Okay, so yes, if you look at the other different organic molecules such as alcohol, as you remember, I have already explained the methyl molecule. But beside it, I'd better explain you some other different parts about it. Hydrogen bond is, I know, very important. Especially hydrogen bond is very important during the preparation of a solution. For instance, let's look at a cup of water. Let's look at a cup of water in the picture. Assume that here there is 1 liter of pure water. Okay. 1 liter of pure water can solve methyl alcohol or ethyl alcohol with different proportions. There is no any yani arkadaşlar hiç sınır yok. Yani istediğimiz kadar biz bunları istediğimiz oranda karıştırabiliriz. There is no any boundary. We can make different kinds of solutions with different ratios. But if you look at the greater molecules, if you look at for instance, let's put more and more methyl alcohols or ethyl alcohols as much as you can. Sooner or later, you are going to see a homogeneous solutions, no problem. But if you look at the greater alcohol molecules, for instance, greater than 5 carbon atoms, let's look at an greater carbon atoms, for instance, with 10 carbon and with 22. Yes. For instance, let's look at this molecule. This is an alcohol, no problem. But in terms of the carbon number in the molecule, this molecule has a greater shape, and the hydrogen bond part is very small if you compare the whole part. For instance, if you look at the methyl alcohol molecule have a little shape, But if you look at the molecule with 10 carbon atom, for instance, that molecule is more and more greater. This molecule is more and more greater, and that part to form hydrogen bond is very small when you compare with the other parts. That's why solubility of that molecule is very, very less than the solubility of the methyl alcohol or ethyl alcohol when you compare with that little molecules. Okay? Ee, Yani arkadaşlar isterseniz burayı bir kere daha anlatayım. Hidrojen bağının bir önemli özelliği de yani hidrojen bağı kurabileceği diğer maddeler arasında çok rahatlıkla çözünmelerini sağlar. Dolayısıyla yani alkol mesela alkoller hidrojen bağı oluşturabilir. O yüzden bir yani saf suyun içerisinde istenilen oranda çözünebilir. Ama burada dikkat etmemiz gereken şey şu. Alkollerin arkadaşlar hidroksit içeren grupları dışındaki yani OH içeren grupları dışındaki büyüklüğü ne kadar? O grupların büyüklüğü daha da arttıkça o zaman tabii arkadaşlar çözünürlüğü ve hidrojen bağı kurma yeteneklerini azaltıyor. Yani bunu da vurgulamak lazım. O yüzden hidrojen bağı kurma yeteneği açısından alttaki molekül, alttaki gördüğünüz gibi işte yaklaşık 10 karbonlu molekül metil alkolle veya etil alkolle kıyaslandığında sudaki çözünürlüğü çok çok daha düşük olacak. Bunu da unutmayalım. Okay. So let's look at the Van der Waals interactions right now. Van der Waals interactions. Okay. So, before looking at the Van der Waals interactions, I want to recall once again. I want to recall once again the non-metal and metal atoms. To understand the difference between van der Waals interactions, first of all, you need to remember easily non-metal atoms and metal atoms. As you remember, there are in general 10 important nonmetals. If you look at the important nonmetals, hydrogen, oxygen, carbon, fluorine, chlorine, bromine, iodine, phosphorus, and sulfur, and also, yes, maybe one more element, nitrogen. In general, there are 10 different nonmetal atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. And you can also add selenium atom, but in general, in the questions, you can't see selenium atom, especially you see that such 10 different elements as non-metal elements. Okay, just after recalling that atoms, uh, I would like to emphasize once again the different type of van der Waals interactions. First one is ionic uh, ion ion dipole interactions. Interactions. Ion dipole interaction recall the non-metal, ion dipole interaction recall the polar and ionic molecules or compounds. Between polar molecules and ionic compounds, you can see ion dipole interactions. For instance, for ionic compound, let's take the sodium chloride, and for a polar molecule, let's take the water molecule. As you see here, water is a very, very polar molecule, and the sodium chloride is also a ionic compound. The interactions between that compounds can be explained with ion dipole interactions. In addition to this, dipole interactions and dipole interactions. Uh, as you can easily realize, for dipole interactions, you need a polar and also polar molecule. The interaction between polar molecules, we can see that dipole interactions. So let's take different types of polar molecules. For instance, water and hydrochlorides, or ammonia, or uh, for instance, hydrogen fluoride and more. Okay. So, in addition to this, you can also see induced dipole, induced induced dipole interaction. This action is very different from the other ones. This is very important to understand that induced dipole, recall the non-polarity. Non-polarity. In other words, if a molecule is nonpolar, that time it has a capacity of having induced dipole interactions. Okay, it is very important. So induced dipole interactions can be seen between nonpolar, nonpolar, and nonpolar molecules. Okay. As an example, I can give you carbon tetrachloride or for instance, bore trifluoride, for instance. The interaction between that molecules, because they are the nonpolar molecules, the interaction between them can be explained with induced dipole interactions. And also, this is very important. In general, you see that interaction as London dispersion force. London dispersion force. In general, you see that induced dipole interaction as London dispersion force. So yes, especially use rather than induced dipole, London dispersion force for that interaction. Okay. I'd better explain more details about London dispersion force because London dispersion force is very different from other ones. First of all, let me show you what the London dispersion force means. Okay, yes. To understand the dipole-dipole interaction is very easy because let's look at the hydrogen chloride molecule and, for instance, uh, water molecule. Okay. If you look at each molecule, they are polar molecules, and if you look at the electron density on the chlorine atom is greater than hydrogen atoms, and that's why it behaves like these molecules at the same time behaves like a magnets. The chlor part of that molecule is highly negative side, and the other part is highly positive side. And also, if you look at the water molecule, it is also same with hydrogen chloride. The hydrogen parts are positive parts, and oxygen is the negative part. As you can easily realize, the negative and positive parts have clump interactions at the same time. Because of clump interactions, they can repel each other. They can attract each other. The opposite parts, attract each other, and the same parts repel each other. That's why there is going to be a dipole-dipole interaction between that parts. So this is the dipole-dipole interaction. Okay. Because of the polarity structure of the molecules, we can see a dipole-dipole interactions between the negative and positive parts of the molecules. This is very easy to understand, no problem. But if you look at the London dispersion forces, it is a little bit different. So let's look at the carbon tetrachloride atom. So carbon tetrachloride molecule. Carbon tetrachloride molecule is a nonpolar molecule. Okay, this is a nonpolar molecule, and if you look at the electron density around the molecule, it's nearly the same. In other words, electron density is nearly homogeneous around the carbon tetrachloride. That's why you can't see any negative or permanent. You can't see permanent negative or positive parts. But if you look at the polar molecules, They are permanent. They are permanent polars, positive or negative. That's why we call that. That's why we call that molecules as polar molecules. But if you look at the carbon tetrachloride, it is non-polar because you can't see any permanent dipoles. But as you remember, molecules, uh, very mobile particles with very high speeds. And when they assume that this is a carbon tetrachloride molecule, okay, assume that this is a carbon tetrachloride molecule, you can see any other molecules. You can see any other molecules. Just close the carbon tetrachloride molecules. As you can easily realize, I know they are nonpolar molecules and they don't have permanent dipoles, but just after coming closer, just after coming closer, you can easily realize that the electron clouds of each molecule will be induced. That's why right now, as you can easily realize, electron clouds repels each other. So during that motion, electrons go to other parts. Electrons go to other parts, and they have right now induced dipoles. That's why that induced dipole parts can be attracted or repelled with other molecules. That's why they have very that's why, because of that structure, during the motions of particles, they have right now induced dipoles, and because of that induced dipoles, they can have London dispersion force interactions between them. Okay, so in addition to this, London dispersion force is directly proportional with London dispersion force is directly proportional with is that London dispersion force is directly proportional with electron numbers, or in other words, total electron numbers of molecule. That's why if you look at the total electron numbers, this is the methane molecule. As you see here, if you look at the total electron numbers for that molecule, if you look at the total electron numbers, one from hydrogens, 4 times 1, and plus 12 from carbon atom. So as you can easily realize, there are 16 electrons in total. But if you look at the carbon tetrachloride, as you can easily realize, carbon tetrachloride have in total 12 from carbon atom and 4 times 17 from each chlorine atom. As you can easily realize, the total electron number of carbon tetrachloride is greater than methane molecule, and we can say that the boiling point of carbon tetrachloride is greater than methane molecules. Okay. You can easily understand it because in room temperature, carbon tetrachloride is liquid, but in room temperature, a methane molecule is gas. You can also understand the strength of London dispersion force when you look at the boiling points or whether it is a liquid or gas in room temperature. You can easily understand when look at that informations. Okay. Arkadaşlar buraya kadar anlattıklarımdan anlamadığınız bir şey var mı? Tamam. As you see here, the London dispersion, the impact of London dispersion force is very important. When you look at the especially halogen atoms, when you look at the halogen atoms and the molecules of halogen atoms, let's remember the let's remember the basic halogen atoms: fluorine, chlorine, bromine, and iodine. The fluoratom may produce, as you remember, fluoratom may produce fluorine molecule, and chloratoms may produce chlorine molecules, and bromine by the same way, bromine molecules and iodine molecules. As you can easily realize, the electron numbers of iodine, electron numbers. In terms of electron numbers, iodine is greater than bromine and greater than chlorine and fluorine. The boiling point is also same. So in terms of boiling point, iodine is greater than bromine, chlorine, and fluorine molecules. You can easily understand it because in room temperature, the iodine is solid. Iodine molecule is solid. Chlorine is liquid and gas, and chlorine is gas with higher boiling points, and also fluorine is gas with lower points. That's why, especially that London dispersion force is very active to understand the molecule structures and boiling points when you compare between that halogen molecules. Evet. Okay, let's look at the others. Let's look at the other interactions. If you look at the other interactions, you can also see it: induced dipole, and ion interactions. And also you can see induced dipole and dipole interactions. Induced dipole and dipole interactions. Ion induced dipole interaction is very rarely seen, and the strength of the induced dipole ion interaction is very low. But if you look at the induced dipole interaction, sometimes its strength is not bad, but evet.
Hocam bekleyenler varmış yine.
Evet, aldım, evet.
Tamam. Kusura bakmayın böldüğüm için.
Ya ne demek. Okay. As you remember, if you look at the induced dipole ion interaction and induced dipole interaction, they are nearly the same. They are the weakest interactions. They are the weakest interactions. In addition to this, I want to summarize that physical interactions, physical bonds, is very important to understand the solubility. Okay, to understand the solubility, to understand the structure of solubility, you need to focus on that physical bonds. Okay, let's look at the let's look at the interaction between solubility. Let's look at the interaction between, let's look at the relation between solubility and physical bonds. Okay, relation with physical bonds and solubility. Okay. Uh, uh, like once like in other words, polar wants polar, or non-polar wants non-polar. This is the best explanation. This is the best explanation to understand the greater solubility ratios. In other words, we can say that polar wants polar molecule, or non-polar molecule wants non-polar molecule to have the greatest yield in terms of solubility. If you look at the water molecule and if you look at the water molecule and methyl alcohol, as you remember once again, the solubility ratio is very high, and you can have different solutions with different ratios, no problem. But for instance, if you look at the water molecule and carbon tetrachloride, because water is a polar molecule and to carbon tetrachloride is non-polar molecule, you can see the least solubility, the highest solubility. This is the highest solubility. You can see here the highest solubility. You can see the lowest solubility here. But if you look at the carbon tetrachloride, and to another non-polar molecule, for instance, benzene molecule. Let's look at the benzene molecule. Benzene molecule, you can also see a benzene molecule like this. I'm going to explain in details when we study the organic lectures. But also, right now I'm going to show you as a non-polar molecule. Benzene molecule, we can call them as benzene. Benzene molecule is a very non-polar molecule, and carbon tetrachloride. That's why, because of their non-polar structure, they have the highest solubility between them. And also ion dipole interaction is also very important. Solubility ratio is not bad, but as you see here, like polar and non-polar is the best. They have the best solubility ratios between them.